Okay, so just a little synopsis, keep the videos a little bit more compact. We got a graph. We just put up a graph. I asked people to estimate the vertex coordinates of the vertex and the y-intercept, okay? People a little slower than I figured in finding the vertex. You got to be able to do that because I'm going to ask you to do that for homework with your data, okay? So the vertex is going to be the point where the parabola, well, it's going to be the axis of symmetry. Now, this is part of a parabola. As we pointed out, the rest of the parabola would go off like this. And at some point, this is going to level out, and when the instant it levels out, that's your vertex. So the vertex of the parabola, represented here, is a little to the left of 160 the way I've drawn it, and up a little bit. So we made an estimate that this point is 158.6. Okay? So we'll accept that estimate. So we want the equation of a quadratic function because, as I've told you, physics predicts that this should be quadratic, and it turns out that it really is. Okay? Very, very close to quadratic. Equation of quadratic with a vertex 158.6 and y-intercept of 0, 170. What's the equation of that parabola? Well, if you know what the vertex form is, you could probably write it down, but we want to kind of analyze this and understand, and we're going to keep hitting these basic transformations. They're essential to understanding functions. Okay? One of the essential things you take out of this course. So, in order to get the equation of quadratic, we know that any quadratic function can be obtained from the y equals x squared function by a vertical stretch, a vertical shift, and a horizontal shift. Y'all showed good skill with that. Acceptable skill, at least on the midterm. So what are the vertical shift, horizontal shift, and vertical stretch that you need to do to the y equals x squared graph? So my question was, what is the most obvious difference between the y equals x squared graph and this? I asked you to draw a y equals x squared graph because people were not giving me an answer to that question, okay? And people drew a good y equals x squared graph, at least most of you. Some of you are a little slow. I didn't give you a lot of time, but I saw a lot of them. So I assume you know that it looks like this. Maybe flatter, maybe sharper, but something like this. What's the most obvious difference between this and this? Well, finally somebody said, well, the axis of symmetry ain't where it was. Okay? Something like that. That's how I said it, wasn't it? Okay, axis of symmetry here is the y-axis. Axis of symmetry here is not the y-axis. That's a really obvious difference. And what you want to do when you look at a parabola, well, actually the first thing you want to do is look at where the vertex is. If you got that information, or at least know whether the axis of symmetry has been shifted. Okay? If the axis of symmetry is not the y-axis, then you do have a shift. Okay? And that would be a horizontal shift. This graph has been moved over from an x squared graph on the y-axis to a graph with an axis of symmetry at the vertex. And this shift that takes you from here to here is your horizontal shift. So in this case, if this is a vertex, this thing has been shifted 158 units in the horizontal direction. And then it becomes a little more obvious that it's also been shifted upward 6 units because the vertex of this one is at the origin. It's on the x-axis, and this is 6 units above. So since the vertex is moved from the origin to the point 158.6, you know what the horizontal shift is, and you know what the vertical shift is. Okay? Now you got to lock that in. You got to understand that. You got to see that when you look at these graphs, and when you look at the graph you made for your data. Okay. So that's what we're saying here. And there's also some vertical stretch, but you can't really spot that. You're going to have to do a little analysis to figure out what the vertical stretch is. Okay? So we're just going to say, okay, there's also vertical stretch. We'll call this vertical stretch factor capital A, because that's what we've always called it. Okay? Now, you got the y equals f of x equals x squared function. You know the vertical stretch and, the vertical shift and the horizontal shift. Well, the first thing you do when you draw a graph is you vertically stretch it. When you transform a graph, you do the vertical stretch. Because if you happen to do the vertical shift before the vertical stretch, you're lost. You're not going to get the right graph. So you always do the vertical stretch first. Now, it wouldn't hurt to do the horizontal shift first, but still we're going to do stretch first. Okay? Stretch before shift. Okay. If you vertically stretch this function by factor a, you get this. We've been over this many times. You want to lock it in now. What do you do for a vertical stretch? You multiply every y value by the vertical stretch factor. Okay? Now the y values are f of x. If you multiply them all by the vertical stretch factor, which is unknown, but we call it a, you get y equals a f of x. And if you replace x by x minus 158, that accomplishes the shift. That's been explained 3 or 4 times why. If you haven't picked up on why by now, you might go back and look again because you remember it better if you know why, but at least know what the rule is. Okay? So, you have this. We get this. We add 6 to every y coordinate. This is the y coordinate before we do the shift. Adding 6 gives us the y coordinate after we do the shift. Okay? Well, f of x equals x squared, so if we replace x by x minus 158, we're going to have a minus x minus 158 squared. Now we've got an a in front of that and a 6 tacked on to the end, but that's what we get. Okay? You could expand that, but you don't want to. Sometimes you do. Right now you don't, because this is the simplest form of the function. So now we know the form of the function, we just don't know the value of a. But y equals 168 now really if we're talking about the flow experiment we'd be using t instead of x, but I started with x because that's the way we originally wrote the function, okay? We really use a t to remind us that we're talking about time. But y equals 168 when x equals 0, because that's what we estimated, right? If you know the coordinates of one point on the graph, you can plug them in, and it'll give an equation with the only one unknown, a. And you'll be able to solve it for a. So, $168 equals a times 0 minus 158 quantity squared plus 6. That's real easy to solve for A. Just square 158, subtract 6 from both sides, okay? And you're going to get A approximately 0.0016. That's not good. I did something dumb. .007, I did a reciprocal, then I reciprocaled again without noticing. Okay? And then I modified it just a little bit to get the .007. Now you can solve that equation, right? Okay? If I gave you that equation to solve, you'd say, oh, that's easy. Okay, you just square the negative 158. Okay? Give you about 225,000. Subtract 6 from both sides, and then divide by whatever that is. Okay? And it'll come up somewhere around .007. Maybe in the upper 006s, maybe in the low 007s. Okay? So you can figure that out. So now, I'm going to switch to T here. Okay? Well, I'm going to ask you to repeat those exact steps for the graph that you make for your data. Okay? Hopefully you've already made it. Because I think it was due today. Okay? There it is. Now you're also going to get an equation by doing the simultaneous equations. You're going to imitate step by step what we did last time for your data. To draw your graph, you're going to estimate 3 points. You're going to get 3 simultaneous equations, and you're going to solve them. Make sure one of your points is the y-intercept. That makes it a lot easier to solve the equations. Otherwise, you're stuck with 3 equations, and it gets a little more complicated. Okay? If you choose the y-intercept, you already know what c is, so you reduce it down to 2 equations real quickly. We'll deal with 3 equations, but first we're going to deal with 2. Okay? You can do it for 2, you can do it for 3. Not that much harder, just a little longer. Okay, so anyhow, there's our equation. And you're going to compare that equation to the equation you get from your data. Okay? And you'll see what that means. To compare them, you're just going to take the t values that you observed, plug them into this equation, plug them into your model from the data, and see what you get and see how close it is to what we actually observed. Okay? If you think that at t equals 20, the depth is 93, well, how close does this come to 93 when you plug in your t? Okay? And for the other model, when you get from the simultaneous equations, you're going to plug in 93. You can use your calculator. You don't have much. It's ridiculous to work that out by hand unless you need practice with your arithmetic. Okay, and that's more practice than you probably need. Okay? Calculators are now legal. So you plug it into your calculator. It's not hard. It doesn't take long. Okay, well that's the procedure I want, because I want you to understand this scheme, this transformation scheme that we've been talking about for 2 months, that you're getting pretty good at. We want to lock it in. We want to build on what you know, which is how to do horizontal and vertical shifts, and in a couple of cases, how to do stretches. Okay? I'm going to build on that and give you a big picture.